All right, recording is rolling. Welcome to Friday, September 22nd. So there's a reunification drill today. We already did that. Actually, it turned out to be not nearly as disruptive as I was imagining it could have been. So we've been able to get some good class time in all the classes so far. So we're gonna make the best use of our time here, which is we're gonna solve some textbook puzzles. What we're gonna do is solve some textbook puzzles. All right, so I think the last place I left off with you guys in the notes was we were partway through number 82, well, the jet on the runway. Okay. So here's what we do. I'm gonna start that one from scratch and then take you guys all the way through to the end. Sometimes you get to see things a second time. Sometimes you see something once and then you go home and sleep on it, come back next day, and maybe it clicks whereas maybe it didn't before. Right? But the premise here is that there's this jet. They told us the weight of the jet and the thrust force from the engines. And they're saying there's some minimum takeoff speed, right? You get so and so fast and then get airlift, right? How much runway? How much runway do you need for all this to come together? How much runway? Right? And there's a bunch of little steps that are involved in this. Now, the big picture is if you're looking for how much runway to reach the speed, that sounds kinematic. Right. But where does the acceleration come from? Well, some thrust force acting on some mass. That's Newton's second law of motion. That's dynamics. It's new stuff we're doing. So we have to juggle both of these, right? We have to juggle both of these. We're going to say the plane gets accelerating by a force acting on a mass. And once we know that acceleration, we can skip over here to kinematic motion and solve for how much runway, like a distance, right? Right. So you guys remember acceleration is like the bridge between kinematic motion and dynamic motion, right? But there's also a bunch of little steps we have to take care of too. Like, for example, the fact they told us the weight of the plane. Well, we're more interested in the mass of the plane, right? So we can know what mass is being accelerated by the thrust force. So let's start with that. Right, the mass of the jet is going to be the weight of the jet divided by Earth gravity. Right? A lot of times I write this rearrange. I'll say weight is equal to m times g. Right? So okay, so now I'm just rearrange that. So the mass of the jet, let's pop in some numbers. Right. They told us the weight was 2.75 times 10 to the 6 newtons. Right. Earth gravity, I'll just round it out 10 meters per second squared like I usually do, which then the mass of the jet, don't even need a calculator, right? 2.75 times 10 to the 5th, and that's kilograms. Okay, great. We know the mass of the jet. Okay. Now if I'm thinking like a free body diagram on this jet, as it's rolling down the runway. Remember, it's not actually flying yet. It's just rolling down the runway. Okay. If I do a free body diagram, I'm thinking this jet has a weight and a normal force that are balancing out. Right? I mean, there's the weight right there. Right? The normal force would be balancing that out. Okay? Right? And then there's some thrust force, F thrust. Right? That's pushing it forward. And we were given that. Now, if we know that thrust force acting on that mass, we can get the acceleration, right? Because that thrust force would be the net force, wouldn't it? Because the two verticals cancel out. Right? So the acceleration of the jet is going to be the net force, which is the thrust force acting on the mass of the jet. Right? No, the thrust force was given as 6.35 times 10 to the 6 newtons. The mass of the jet we just found right here. 2.75 times 10 to the 5th, and that's kilograms. Okay? Now the fact that my force is in newtons and my mass is in kilograms means that when you divide those two, the unit will naturally come out to meters per second squared. Right? So 635 on 275 times 10. Do that one. Yeah. Okay. So I'm looking at 23.09, and that'd be meters per second squared. Right. Now, truth be told, that's too much precision, but maybe I'll save my rounding for the end. It's usually good stuff to do. Right. Right. So now we know the rate the jet's accelerating. Right. Guys, for context, how many G's is that approximately? How many?
230.
Yeah, like 2.3, like 2.3 G's, right? Because I know here's how you do like dimensional analysis. You could say every 1 G is about 10 meters per second squared. So like 2.3 G's.
motion, teachers. Please take a moment to review the list of students who need to do the retake for testing. We are missing a lot of those students in the media center, and we need those students down to try and achieve their concordant score. Please take a look at that list sent out by Ms. Brady and send those students down to the media center. Thank you.
All right, let me go ahead and pause this recorded and check on that real fast. All right, recording is resumed. All right, so we're back here. So just for fun context, yeah, if you were inside that jet, you would feel about like almost 2.5 times your weight just because of the thrust force, like horizontally. Right? I guess if you wanted to combine with Pythagorean theorem, the fact that you have your actual weight pulling down, feel even a little bit heavier than that. Right? But that's just a side thought. Okay, so what we care about is 23 meters per second squared. Right, now let's kick over to kinematic motion. I like to set up a tax BD table, just a checklist. If you like this framework, great. It's not, but at least it's a possible way to think about this. Right, what do we have? What do we want to know? Okay. Well, we just found the acceleration. It's like 23.1 meters per second squared. Right. The question is how much runway. So we're solving for this. Right. And the final, that's what else we gotta do. I almost forgot that. They did tell us the speed the plane has to get up to, but they gave us in kilometers per hour. You guys remember they gave us kilometers per hour? So if we want meters per second here, we do have to do a conversion. Let's go do that. 285 kilometers per hour. Right? Guys, how many meters in a kilometer? 1,000? 1,000 meters and 1 kilometer. Right? How many seconds in an hour? Like 3,600? Right. Or if you like, you go 60 seconds in a minute, 60 minutes in an hour, you'll still get that. Hey, look at there. Meters per second. You guys see meters per second? Of course, we want the speed to be in meters per second so that we can just apply those kinematic equations. Right, so 285 times 10 on 36, it'll work out to. I'm looking at 79.17 meters per second. That's this number right here, 79.17 meters per second. Okay, so we got to get up to that speed, accelerating at that rate. Okay. Oh, how many kinematic variables do you have to solve this? 3, right? So is there something else that's maybe implied that you actually could know? What else could you actually know that might be implied? Can you figure this out? Because if you take physics in college, physics textbooks love to imply a variable here or there, and you have to sort of figure out. Is this jet starting from rest? Probably starting from rest. Which means this number is like 0 meters per second. There you go. Right. So like that. Okay. So now we know what we have and what we want to find out. Gotta go over to these 3 amigos right here. Which one will lead directly to the answer? Which one leads directly to the answer? How much runway do we need? Which first, second, or third? Yeah, the third. You guys saying the third one? Yeah, I like the third one too. The third one is the one that doesn't mention how much time is passing, and we also don't quite know that or want to know either, right? Yeah, the third one we can get it all in one shot. Now, alternatively, you could have used the second one to solve for the time, and then taken that time and popped into the first one and solved the runway that way. Right? I'm just going to use the third one, do it all in one shot. So final velocity squared equals initial velocity squared plus 2ax. Okay? And we want to know, what is x? What is that runway distance? Okay? We know we're getting up to 79 point something meters per second. So square that. It's going from 0, from rest. Whatever, that goes away anyway. Okay. Plus 2 times, and we're getting there at 23.09 meters per second squared. Okay. And then x. Okay. I guess you have that all decent right there. Like that. Okay. All right. So I think x is just going to be, if you like it in terms of variables, it's just going to be the final velocity squared divided by 2a. Okay. But for our numbers, that's like 79 meters per second being squared divided by 2 times 23 meters per second squared. Rounding a little bit just because save a little space there. Okay. But maybe in my calculator I'll add some precision to it, right? So 79.17 squared divided by 2 times 23.09. Okay. Looking at 136, maybe I'll just round to that nearest meter. Okay. 136 meters. 136 meters. All right, there you go. So if that runway is like 200 meters long, then that's enough runway. If the runway is only 100 meters long, well, now we got some trouble. Okay. Right, you guys get that? Right. Next question, number 92. Oh, look, it's the classic Atwood. Classic Atwood. This was the last lab that you guys did. Classic Atwood. Okay. So they told you the two masses are 3 kilograms and 5 kilograms, and they got 2 questions. The questions are, what's the tension in the rope and what's the acceleration of the blocks? Right? Now, the fact that they asked what is the tension first and then what's the acceleration second is a big hint to me that there's a particular way they want you to solve this. And I'm actually going to solve it the other way with you guys. So we're actually going to solve question B first and then go back to A. Okay. But let's look at the poster version of this. Yeah, this is the last lab that you guys did. Okay. So 2 different masses, therefore 2 different weights. Right? Oh, and again, the 2 questions could be like, what's the acceleration? Right? And then what's the tension in the string holding this together? Okay. Now the acceleration, so a lot of textbooks will phrase it like, what's the downward acceleration of the large block, or what's the upward acceleration of the small block? But it's the same magnitude, right? Because they're tied together with the string. So they're both the same magnitude of acceleration. Right? Okay. And I think the way that your textbook wants you to solve it is like from what I've been calling like a micro point of view too. To focus on this block individually and this block individually and create a system of equations between those, right? So they would actually start with these bottom 2 boxes. What they say is the net force on block 1 is driving mass times acceleration of that block, right? So the net force would be the tension force up minus the weight down, right? And then there's your net force. Net force equals mass times acceleration, but only for that individual block, right? Then do a similar setup for block 2. Say, well, the weight down minus the resisting tension force up. There's your net force, which is driving block 2 down overall, right? And then you have a system of equations with, you wouldn't right away know what the acceleration is, and you wouldn't know what the tension in the string is, but you would know everything else. You're allowed to know M1 and M2, and you're allowed to know the gravity field, okay? You could solve it that way, right? But the way I'm gonna take you guys through it in the notes is actually a different perspective. We're gonna do like a macro point of view, okay? So I'm gonna start with Newton's second law of motion as it applies to the entire system. And from a systems point of view, these 2 weights are external forces, saying let's go clockwise versus counterclockwise. And the tension is just internal to the system. So I can skip right past that. It's just holding everything together, but it's not actually an external force, right? Okay. And then you can get the acceleration from that. It's net force on total mass. This was the answer to your guys' lab. Okay. And then from there, once you know the acceleration, you can pop into one or the other. And either way, you can get the tension. It'll be the same way either way. I will show that to you guys that the tension is the same either way you do it. Okay, so your textbook has, I'll call this mass B is like 5 kilograms. Let's say mass A down here, mass A is like 3 kilograms. Okay, so you got 3 kilograms versus 5 kilograms. Okay, that's probably good practice to go ahead and set up a free body diagram anyway. So I'm going to do that. So the weight of block B is about 50 newtons. The weight of block A is about 30 newtons. Okay, you guys see the relative sizes of those, right? It's like 30 versus 50 units. Right? 30 newtons versus 50 newtons. Right? And then there is this tension force on each individual block that's internal to the system as a whole. That's a lot of times I'll call this like a Goldilocks type force, right? It's larger than the small weight, but it's smaller than the large weight, so that there's a net force upward on the small block and a net force downward on the large block. Right? Now we don't know what that tension force is, right? But if I had to make a guess, it's somewhere between 30 and 50 newtons. Maybe I'll say like 40 newtons. Okay? And how these Atwoods work out, having done many of them over the years, it ends up being a little bit less than that. So it's probably going to be a little bit less than 40 newtons. That's what I'm guessing. Okay, a little bit less than 40 newtons. Right? But we're going to find out for sure. Okay, let's do my systems point of view. So the acceleration, like system as a whole, like clockwise versus counterclockwise, we got net force, net external force on total mass. Okay? So there's a competition between 50 newtons saying, let's go clockwise, and 30 newtons saying, no, let's go counterclockwise, right? Except for the net force. And guys, how much total mass is being moved by that net force? 5 kilograms plus 3 kilograms, right? Right. So this net force is driving both of those blocks, right? Right. That makes sense. Okay. Pause for a moment here. What if they were the same mass and therefore the same weight? What would the net force be, like external in the system? It would be 0. Which means that it would be equilibrium and there would be no acceleration at all, which makes sense too. Probably aligns with maybe you tried that in your lab. Right. So in this case, we got 20 Newton net force acting on 8 kilograms. Right. That's like 2.5 meters per second squared. Okay. Right. And remember, make sure you have a unit attached to your number. You can't just say 2.5, right? You guess it 2.5, okay, oh, meters per second per passing second, right? Meters per second squared. Right. That is actually question B in your textbook. That's the second question they asked, right? The first question they asked is, what's the tension? But we're going to take this and plug it into, say, one of these expressions here to get the tension, right? I'm going to do both, and I'll show you that the tension works out the same either way you do it. Let's start with mass A over here. So if I just set it up for a block A, just for block A, okay, I can say the net force on block A is equal to mass A times acceleration, right? And the net force on block A is the difference between these two. The tension force, which we still don't know yet, minus the 30 newtons down. That's going to result in this 3 kilogram mass accelerating at 2.5 meters per second squared, because we did figure that out. Right? Right. This would be up, of course, it's accelerating upward. If the up force minus the down force, right? Oh, well, all I have to do is just multiply that right there and add over 30 newtons. Guys, if you have 3/4, how much money do you have? 75 cents. So what's 3 times 2.5? 7.5 plus 30. 37.5. Guys, that's 37.5 what? Newtons. All right. Newton. Hey, remember I made a prediction before we started plugging and chugging? I said it's going to be probably about 40 newtons, maybe a little bit less than 40 newtons. Hey, it is a little bit less than 40 newtons. Look at that. So it's like the Goldilocks force. Okay. All right, like I said. Let me do that exact same thing, but from block B's perspective. And I bet I'm going to get the exact same tension from block B's perspective. Let's see if that actually works. So I can say the net force on block B is mass times acceleration for block B. The net force on block B, well, I got the weight of block B pulling down, that's 50 newtons down, minus the tension force pulling up, which we know what it's going to work out to, but let's say we didn't, right? We're going to solve for it. Okay? That's driving block B 5 kilograms to accelerate downward at 2.5 meters per second squared. And the way I set this up, I have down as the positive direction, right? Down minus up. So I can call this a positive value for the acceleration also. Okay. Ooh, if you have 5/4, how much money do you have? Like $1.25, right? Therefore, what is 5 times 2.5? Is that like 12.5, I think, right? 12.5. Here, but let me check. You guys got calculators, right? 5 times 2.5. Yeah, 12.5, right? That's floating decimal place kind of. Right. So I can add the tension over, subtract the 12.5 over. The tension force is going to be 50 newtons minus 12.5 newtons. What is 50 minus 12.5? Hey, it's 37.5 newtons. Exactly like it should be, because there's only one tension in that string. One tension in that one string. Applies to both. Oh, yeah. Sorry, go. No, I'm doing a little bit of overkill. I'm just showing you guys that no matter how you did it, you would still get the same answer. Yeah. So yeah, if this was like suppose you go to college, you're taking a test, and they say what's the acceleration and what's the tension. yeah, you could just do that and say, okay, you got the answer. Yeah, do that. Yeah. Great. Okay, so you guys get there? How are we doing on? I've got 43. Okay. All right. You know what? That's as far as I got in the shortened class earlier today. So let's take the rest of class and just solve some more Atwoods. Right. So these are pretty fun anyway, right? Right, these are pretty fun. So we'll get some bonus questions here. Set up some bonus Atwoods. Right. But it'll be the same two questions over and over. What is the acceleration and what is the tension? Okay. So how about what if I make them really close to each other? Like what if this guy is 11 kilograms and this guy is 10 kilograms, right? 11 kilograms versus 10 kilograms, right? Even before you solve anything, you probably get a good conceptual idea of what these answers are going to be. What is the acceleration and what is the tension? Right, there's the two questions. Right, I bet, guys, or maybe I should ask you guys, is this going to accelerate closer to 0 meters per second squared or closer to pure free fall? What do you guys think? Closer to 0, right? Because they're almost balancing out, not quite, but close, right? And hey, if you had to guess a tension in the string holding these two, who wants to guess the tension in the string? It's somewhere between how many newtons? Like what's the weight of 10 kilograms right here? What's that weight? Is that 100 newtons? And what's the weight of 11 kilograms? Yeah, 110 newtons, right? Right. Ooh, so this one's a little bit bigger than this one, but not by much, right? Oh, and if the tension force in the string is like the Goldilocks force, ooh, what's a pretty good guess for the tension force? I'm gonna get, okay, well, the average of those is 105. I remember the last time we solved an Atwood, it was a little bit less than the average. I'm gonna say 104. 104 newtons. I don't know that's the answer. I'm just making a guess. I'm gonna guess 140 newtons, but we're gonna find out. So let's do our process. Let's do our process here. Right. Hey, you know what? Let's do a micro point of view. Let's set up a system of equations like your textbook probably wanted you to do anyway. Right, so I've got let's do two equations with two unknowns. So I'll set up the net force on this guy is mass times acceleration. And the net force on this guy is its mass times acceleration. Oops, mass B. Okay. So that would look like, see, the tension force up minus 100 newtons down results in 10 kilograms accelerating at some acceleration value. Okay. And for the other block, I got the 110 newtons down minus the tension force up results in 11 kilograms accelerating at some value, right? You guys see a system of equations? So I'll call it a system, right? Like an algebraic system, right? Two equations with two unknowns, right? So yeah, this is like the other way of doing it. The last one I solved with you guys was like from a systems point of view. We found acceleration first and then found the tension. Right? But what if we did it this way? What if we set up a system of equations? You guys solve system of equations in algebra? Okay. Right, so let's try this out. Maybe I could do like maybe we could solve for the tension in terms of like another expression and then do a substitution, right? We could do substitution or elimination. I guess either way, right? So if I take that first one, I got the tension force is equal to 10A plus 100. I'll go ahead and drop my units just to simplify this a little bit. And then this other one, I got 110 newtons minus that tension force equals 11 kilograms times acceleration, right? But where that tension force is shown up right here, right? Well, from the first expression, I rearranged it and got this value right here. So I can take this and just substitute right there. 10 acceleration plus 100 units. Could be like that. Right. So see, all I did was I took the first equation for the first block, rearranged it to solve for tension force. Right, so that is not just rearranged. Then substitute it, bam, right there. Right, and now I can solve for the acceleration that way. Right. And hopefully this acceleration is closer to 0 than 10 meters per second squared, but we're gonna find out. So what's 110 minus 10a minus 100, because I distributed that negative, right? Let's go to 11a. Okay. I'll add 10a over that, because that's 10 units here, 110 minus 100. And that's 21a on this side. So 10 divided by 21. Acceleration is 10 over 21. That'd be meters per second squared if I restore the units. So that's like 0.4 something meters per second squared. Yeah. So between 0 meters per second squared equilibrium and 10 meters per second squared pure free fall, this is definitely a lot closer to the end of the spectrum that's like 0, right? Okay. So there would be one answer. Okay. Now the other question is, what's the tension in the string? Right? Remember, I was guessing it'd be about 104 newtons. I don't know that's the answer, but we're about to find out. Okay. We can take this known acceleration now and plug it into either one of these expressions and get the same value for tension. Or I could do my substituted value right here. Here, how about that? How about this one? Because it's rearranged, it's already ready to solve it. The tension force should be 10 times the acceleration. So I'm just taking this and point right there. Right. And the acceleration now is 0.476 meters per second squared. Right. Plus 100, and the like newtons. I think this is kilograms here. This is newtons here. Right. Let's see what that is. What's 10 times 0.476 plus 100? So the tension force is 104.8 newton. Hey, remember I was guessing it was going to be about 104 newtons? Pretty dang close. Right? That makes sense. All right. See that? All right, let's do one more Atwood. What if instead of being really close in value, what if the two blocks are very different in value? Like, what if this mass is like 10 kilograms, and this mass is a little tiny, only like 1 kilogram? Right, so 10 versus 1. Okay. But let's go back to like a systems point of view, like a macro point of view. Okay. So each of these guys has a weight, but now they're really different weights. This guy about 100 newtons pulling down there. This guy is like 10 newtons pulling down right here. Right? Right. And then there's some kind of internal tension. Something like that. Right. F sub T. Actually, that tension force is not really drawn on a scale when I'm looking at it, but it's somewhere in between. Okay. All right. So let's do acceleration for like from a systems point of view is the net external force divided by the total mass. Okay. So this is the first way. This is normally how I solve it. Do you guys see these two competing? That's like 100 newtons versus 10 newtons. And ooh, guys, what's the total mass? 11 kilograms. Right? 10 plus 1, right? Because they're both being moved by that net external force. So that's 90 Newton net external force acting on 11 kilograms total mass. Let's see, what is that? That's 8.18 meters per second squared. Oh, I meant to ask you guys before I started. Okay. The fact that these are like so, these masses are so far apart from each other. One's a little tiny, one's really big. It should accelerate what, closer to 0 or closer to free fall? You guys would have said closer to free fall, right? Because we almost got an empty string over here, relatively, right? Yeah, that's getting pretty dang close to 10 meters per second squared. Right? The other question is then, what's the tension in the string? So here, maybe I'll pick let's pick the 1 kilogram block. How about that? Figure out what is the tension in the string. I can say net force is mass times acceleration for that single block. The net force is going to be tension up minus weight down is equal to, well, in this case, 1 kilogram is being accelerated at 8.18 meters per second squared. So there's 8 newtons here. Add over the 10 newtons. The tension force is, that would be 18 newtons. 18 newtons. All right, yeah, that looks about right. 18 Newton tension force. Okay. Could have done it for the other block, the larger block, and still would have gotten the same answer right there. All right. All right. Okay. All right. I think it's a pretty good pause point today. We just got a minute left of class here. So yeah, that'll be a good pause point on the week.